Okay, we're at part three of this chapter 20 uh, lecture series, and we're going to be talking about um, reflection of sound. So reflection is a process in which sound encountering a surface is returned, often called an echo. Multiple reflections are called reverberations. Most of this semester, in fact, I guess all of the semester, you can probably hear a little bit of reverberation in my lectures because we've been having some work done on the house, and so this room that I record in is there's no furniture in it, there's no curtains on the window, and so you get these reverberations. So once we do put furniture, we put a bed in here and maybe some artwork and stuff, it'll deaden the sound quite a bit. I used to work in a recording studio, and the walls were covered in just like fabric with some batting underneath, just to kind of deaden the sound a bit. I remember going to Zaz Studios on Commerce Street, no longer exist. When I walked into that recording studio, the ceiling and walls had these cardboard egg cartons taped to the ceiling, or not taped, stapled to the ceiling and walls to kind of deaden the sound. But in this next slide, we'll see a true anechoic chamber. This is at Southwest Research, where I used to work. This is in the Applied Physics Division. And these panels, you can see, I mean, there's no parallel walls. You get these cones that absorb all the sound waves. Now, what you can't see is here, this is actually a screen. So the cones are also underneath. If you could see through the screen, you would see the same cone mechanism throughout this room. It's a very large room. Now, when you walk into this room, which I have done, I'm retired from there now, so I haven't done it lately. But when you walk into this room, you can actually feel the pressure decrease, because you're always hearing, there's always sound pressure on your ears. Well, when you walk into this room, there's very little pressure because all of the sound is absorbed. It's a very quiet room, and you can actually feel the lack of pressure on your ears. It's a very strange feeling, and it's very, very quiet in that room. When I was a young man, I used to do a lot of spelunking, a lot of cave exploring. And in movies, they show caves as being very having lots of echo, a lot of reverb. That's not the case in the caves I went to. They're very, very dead because the walls are so rough, and so the sound gets absorbed very easily. Anyway, that's not. This is nothing that you're responsible for. I just thought it was interesting to see what an anechoic chamber looks like. All right, let's continue with the lecture. Reverberations are the best heard when you sing in a room with carpeted walls, hard surface walls, open windows, or none of the above. Well, if you've ever sang in the shower, it sounds pretty good. Rigid walls better reflect sound energy. Fabric is absorbent, and open windows let sound energy escape from the room. So hard surface walls are the best for reverb. Consider a person attending a concert that is being broadcast over the radio from microphones on the stage. The person sits 45 meters from the stage and listens to the radio broadcast with a transistor radio over one ear and a non-broadcast sound signal with the other ear. In other words, he's listening to the live concert. Further, suppose that the radio signal travels all the way around the world before reaching the ear. Now, which signal will be heard first? The radio signal, the non-broadcast sound signal, or both at the same time, or none of the above? Well, it's kind of a trick question. There's no way to automatically calculate this off your head. So here's the explanation. Both at the same time. A radio signal travels at the speed of light, 3 times 10 to the 8 meters per second. Time to travel 45 meters at 340 meters per second is approximately 0.13 seconds. Time to travel 4 times 10 to the 7 meters, which is the Earth's circumference, at 3 times 10 to the 8 meters per second is approximately 0.13 seconds. Therefore, if you sit farther back at the concert, the radio signal would reach you first. The other day, my son called from El Paso. He's a political science professor at UTEP, and we were talking on my phone, and I had to take the dog for a walk, but I still wanted to hear what he was saying while he spoke to my wife. So I added my wife's phone to the conversation, and as we were talking, I could hear my voice. Of course, I'm the one speaking, so I hear my voice right away. But then I would hear like not quite a second, less than a second delay. I'd hear my voice a second time on her phone. It was kind of a funny experience. Anyway, that's just a funny side note. Okay, here acoustics. The study of properties of sounds. Example: a concert hall aims for a balance between reverberation and absorption. Some have reflectors to direct sound, which is also reflect light. So what you see is what you hear. If you look up here at these panels, these look like they're maybe fabric or something like that. But these panels here, these are very reflective. You can see the position of the orchestra players here on these panels. So as the sound goes up, it bounces here and comes out at you. Oh, look here. Here's remember in a previous section on this chapter, it was I was talking about pipe organs, and here you can see the pipe organs, and you can see that they're varying length. We're going to get resonances with those, and I think we're going to study that in more detail in chapter 21. Okay, and that's the end of this section.